Well, welcome back. This is General Relativity, Lecture 18. And in here I will endeavor to tell you something about gravitational waves. So what we're doing here is hitting some of the high points in Chapter 7 of Carroll's excellent text entitled, what is it entitled? Here we go. Space-Time and Geometry, an Introduction to General Relativity. Yes. And as you can see, I have the international edition. Once upon a time, as I've mentioned, I had the hardcover, and then sadly I lost it. Of all the books I've lost, I perhaps regret that one the most. But anyway, still not sure what happened to it. Anyway, so we're again studying the weak field limit of general relativity, but this time not with the assumption of static. So we want to look at sort of linearized gravity, where you're looking at the metric is the Minkowski metric plus a little piece, and that little piece is comparatively small compared to the Minkowski piece. And because we're just working to first order in H, the inverse metric, you can just get by, Minkowski upper mu nu minus H upper mu nu like that. So that's kind of nice. Because when you multiply these two expressions, you get things that simplify to the identity matrix, and then this times this cancels that times that, and then finally you get a thing which is second order in H, which we ignore. So that's why that's the inverse. And, just a note, Carroll does entertain second order formula on page 307 and 315, where he calculates energy loss due to gravitational radiation. Maybe we'll have a little bit more to say about that at the end. Probably won't work out the details there, but I do want to discuss it, at least in words. So now conceptually, we can think of this as like a flat space-time where we've got a field h mu nu which propagates. So this is the kind of conceptual model to use for understanding gravitational waves, as it turns out. You think about it, sort of out in the vacuum, where things are mostly flat, and then you've got this ripple, and the ripple is somehow being encapsulated by this perturbation, h mu nu, all right? And so you've got local Lorentz transformations to work with. You could transform h mu nu by this, and he does mention if you were to study gravitational waves in cosmology, then you'd have to use a background metric, which wouldn't be the Minkowski metric necessarily. It could be one of those, metrics we set up for the universe in bulk. And that's the kind of thing you would use to try to analyze, say, waves traveling through the background of space-time in different epochs, right? But anyway, let's see here. That kind of ties into the next lecture, where we'll talk about different models of cosmology. And so, let's see here. First of all, the question then is, what are the equations of motion for this perturbation? Let's see if we can derive the wave equation here, basically. It takes us a little bit, but we'll get to it, all right? And then, let's see here. So, first of all, because the eta piece is constant, differentiates to 0, you're just left with the h's. And so, to first order, you're just left with this expression. And then, to calculate the Riemann tensor, you remember that the Riemann tensor, well, you may or may not remember, but you should. The Riemann tensor had 4 terms in it, right? And the last 2 terms are quadratic in the connection coefficients. And being quadratic in the connection coefficients here is tantamount to being second order in H, which we're ignoring. So we've got this and that, and then remember we can expand the connection coefficients like so, here and here. Although I haven't expanded that one, I've just written it like that. And then, let's see here, so doing a calculation, right? So this goes to this. Let's see what's going on here. I'm contracting over the delta index here, and I traded this contraction of etas. See the sum over lambda here? So I traded that for a delta mu delta, Kronecker delta mu delta. And sorry for the use of delta in these two different ways. You'll forgive me, or you won't. But I mean, sorry. Anyway, not sorry. All right, let me get through this jibber jabber. So it's a pretty straightforward calculation. Basically, you just, inverse metric is your Kronecker delta, and then I just wrote these three terms again, I believe. Boop, 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 beep, bop, boop, yeah. And then same thing happens over here, although I haven't written it. I mean, I'm just copying this down again. And then I thought about it, and I was like, okay, so basically this term over here, it's the same as this term, but with rho replaced with sigma and sigma replaced with rho. So if you think about that, in this term over here, which I haven't read out in any detail, there's going to be a corresponding partial sigma, partial rho. But since the partials commute, this piece will cancel with an unwritten term here, and it'll just leave you this and that, right? And then the corresponding ones with rho and sigma flipped. So, but with a minus, because of minus, right? So I get rho partial nu, h sigma nu, sigma mu. So that gives me correspondingly minus partial sigma partial nu, h rho mu. So that's the rho sigma flip-flop of that one with a minus. And the same thing happens for this one. This is literally that. And then there's the rho sigma reversed term with the opposite sign over here, like so. So you get these four terms, beep, bop, boop, bop, for the Riemann tensor. All right. And great. What's next? Well, so let's put that down on the floor. Keep it out of the way here. So we just calculated. What did we calculate? Well, we calculated that the Riemann tensor has this lovely expression in terms of second derivatives of the perturbation. All right? And I think it makes sense if you just take a step back and think about it. So we're talking about a space which is flat, except for this ripple from the permutation, right? But rather from the perturbation. And so it makes sense that the curvature is totally due to that perturbation, all right? Now, the Ricci tensor we formed from contracting over the first and the third indices of the Riemann tensor, like so. And so I have kind of indicated how this contraction goes with some color coding. In particular, the blue piece comes from this blue calculation right here, which is, so I'm contracting over rho and, I'm contracting over mu rho. And so that ends up basically contracting the partials, which gives you a D'Alembert, a box, which is a fancy notation for minus partial t squared plus partial x squared plus partial y squared plus partial z squared. What? The donuts have arrived. Mm-hmm. Oh, that's wonderful. Yeah. Why, thank you. The donuts have arrived. Ooh. Thank you, Benjamin. We'll eat these later. What? We'll eat these later. We'll have them later, okay?
Okay.
Okay.
I have one when I want to.
Yeah, okay, yes. Mommy may have something to say about that. I don't know. All right, so anyway. So this gives us the D'Alembert, which is minus partial t squared, plus the Laplacian, is what we'd usually call it, the nabla squared, the partial x squared, plus partial y squared, plus partial z squared. Anyway, so that second order differential operator, which we denote by box, that's what comes from contracting the rho and the mu here. And then contracting rho and mu here ends up just tracing the perturbation, which we write at h for the contracted h alpha alpha like that. So this is the so-called trace of the perturbation. And then you've got these two terms, which are just coming from, contracting over the first and third indices, namely rho and mu. So like that, sigma sigma, and over here sigma sigma. But you notice that this one's got a mu derivative, a nu derivative, whereas a mu component, whereas this one's got a mu derivative and a nu component, so they're not the same. You have to write both of them. All right, so there you go. There's our expression for the Ricci tensor in this linearized gravity. And then we can calculate the Ricci scalar by contracting once more, right? And when we contract, what happens is you get yourself two of these guys and two of those guys, and so the two, it cancels to the half and leaves us this lovely expression just like that. All right, great. So then that brings us to Einstein's equation, right? So what's Einstein's equation say? Well, I mean Einstein's tensor first. So here's Einstein's tensor written in terms of the perturbation. It's got all these terms because it's the Ricci tensor minus 1/2 eta mu nu r, and the reason not g mu nu here is because we're working first order in h, right? So the r is proportional to h, so putting the h term in here would be second order in h, so we're neglecting it for now. I mean, we'll be neglecting it explicitly in this lecture. That much is true. And all right, so then at this point, Carroll enters a lengthy discussion on how to decompose the perturbation into several component objects, which are generally highly interdependent. But there exist several choices of gauge which we can fix to eliminate the freedom in certain equations as it is convenient for various applications. And I'll jump to the end where we learn on page 279 to define the 0, 0 component to be minus 2 times the gravitational potential. H0i is this vector wi, and Hij is twice the strain tensor, the traceless strain tensor, minus 2 times another scalar field called psi, delta ij, where psi is defined to be a sort of trace of the perturbation in the spatial sense, weighted by minus 1/6, and the Sij is this traceless so-called strain tensor. All right, so this is just these are just notations to sort of sort through what's the details here in the H. Now, all right, so going on here. Going on. So here's what the metric looks like in terms of all this jibber jabber. You got your scalar, your three vectors, wi, your traceless strain, your scalar psi, and so here's your linearized gravity metric, like so. All right, so the notation above is a decomposition of the metric perturbation h mu nu. On page 280 to 283, Carroll examines the equation of motion for the fields phi, the vector wi, the strain Sij, and psi along geodesics, as well as the form of the Einstein tensor g mu nu as it is expanded in terms of these fields. It looks like this. The 0, 0 component is 2 nabla squared psi plus partial k partial l skl. And then he explains the utility of various gauges. So the thing is, there's freedom in defining the h which is not physical, let's say. It doesn't lead to differences in the measurable curvatures. All right, so like essentially you have different gauges that you can pick here. It's called gauge freedom. So there's this transverse gauge where we look at this derivative of the strain and this derivative of the vector being 0, and it leads you to have this form of Einstein's equation. G00 is twice the Laplacian of psi, which is equal to 8 pi g t00, and G0j is minus 1/2 the Laplacian squared of the vector, plus twice the time derivative of the space derivative of psi, plus 8 pi g t0j. All right, great. And also Gij is all of this. Okay, so it's all right, it's a lot, but Turns out a lot of these things are going to end up being 0. Well, one thing at a time here. So this is what the Einstein tensor looks like in the transverse gauge using this decomposition of the perturbation into these fields that Carroll sells us. All right. Then he also mentions that there's this synchronous gauge. You could put phi equal to 0 and set the vectors, the vector wi equal to 0, and then in the synchronous gauge, the metric has this particularly beautiful form. And then he says there's also a Lorentz harmonic gauge where you set the sort of Minkowski derivative sum of h upper mu nu, I don't know what to call this thing, minus 1/2 partial nu h. This is the trace of the perturbation equal to 0. All right, so now if you don't have enough of a physics background, these ideas about just setting a gauge, they're really perhaps foreign. It's a foreign idea to math students, I think, unfortunately. And you see it a little bit in introductory physics in your ability to choose a different place for the potential to be 0. But it turns out when we're solving Maxwell's equations for like a potential, all right, for like a vector potential or a scalar potential, there's a lot of flexibility there. You can you can shift both the scalar potential and the vector potential by quite a bit and not alter the field equations. And so it's most like elegantly written. The most elegant way to explain what I'm explaining is perhaps this: is the field tensor is the derivative of the one-form potential, right? So that the Faraday, which is the electric and magnetic fields in it, it's the exterior derivative of the one-form potential. And the thing is, you could say A prime is equal to A plus the exterior derivative of some function of space and time, say lambda, right? And you'd still get that dA prime is equal to dA, right? So this is an example of gauge freedom. The fact that you don't have a unique choice of potential which gives you the field strength, right? And in the same way here, we don't have a unique perturbation which leads us to the curvature, which is ultimately the thing which is physical. That's the philosophy here, I believe. And so anyway, I don't know if that helps or not, but that's what's going on here, is that you have there's some freedom in the equation, so we can impose constraints, and imposing those constraints may or may not make the equations easier to solve. At some point here, I'll jump back to my own relativity notes, and we can contrast how my professor did it when I was an undergraduate versus what's going on here. Let's see here. I'll save that for the end. Let's finish Carroll first. So we work in the rest frame of dust, where T mu nu can be written, the stress energy tensor can be written as density and then 0 pressure. And Einstein's equation in the transverse gauge for static sources, we drop the time derivative term and then obtain, let's see here, so page 3. Where did it go? Over here. So if we go, curses. So we were transverse gauge and static sources. So transverse gauge, static sources. Golly. So he says Nabla squared psi is 8 pi g T0, 0, okay, that makes sense, right? Because that's T0, 0 there, you put that T0, 0, there's your 8 pi g. Now there's a 2 delta squared on the other side, right? So that 2 divides over to give you this 4 pi g rho. Nabla squared wj equal to 0. Let's see if we can see that one. That one's coming from this one here, so it's static sources, so that's 0. And so you get minus 1/2, and then T0j is 0, so this gives us the Nabla squared wj is equal to 0. And then down here, well, this is 0 because it's got a time derivative. That's got a time derivative, so it's gone. So we're just keeping this term and that term. Cool. And again, the box becomes a Nabla squared because we're assuming time derivatives are 0. So the box has got a second time derivative as well. All right, so in the transverse gauge, Einstein's equations simplify it to these guys. He says we seek non-singular solutions which behave well at infinity, so we can put w to be 0, we can put, let's see here, Nabla squared. Oh, he says take the trace. If you take the trace of this equation, that knocks out the traceless piece. And so you just get, and when you take the trace of that, that knocks out this piece as well, I think. Or does it take that out? Or does it? Well, I think we're tracing over 3 indices, so that becomes a 3. And so 3 minus 1 is 2. All right, great. So we get 2 Nabla, because this becomes Nabla squared when you trace it. So we get 2 Nabla squared psi minus phi minus psi equal to 0. So that implies that phi is equal to psi, but we know that the phi behaves a certain way in the Newtonian limit, and apparently psi is the same as it. And then finally, since these are equal, that then gives us the Nabla squared. The strain is equal to 0, which means that the strain should be equal to 0 for a nice solution. All right, so then going back to 3 and plugging in everything we just learned, we have that the metric in this linearized gravity in the transverse gauge looks like ds squared is minus 1 plus 2 phi plus 1 minus 2 phi times this, well, the metric for R3, I guess you could say, Euclidean R3. Anyway, dx squared plus dy squared plus dz squared. And in fact, then we can see, so if you peel off the minus 1 here and the 1 here, that gives you the Minkowski metric, right? And then plus terms with phi. So that means that h mu nu is this minus 2 phi, and then you get this minus 2 phi, minus 2 phi, minus 2 phi. There's your perturbation. So as it turns out, that is the form of the perturbation in this weak field limit, where Nabla squared phi is 4 pi g times the density. And it's interesting to notice here that in the previous chapter 4, we just derived that h0, 0 was minus 2 phi. Now we've also got the hij's as well, right? And so we did that back in chapter 4 to like set the scale, if you will, for Einstein's equations. So this is kind of an extension of that calculation in some sense. All right, so moving on here. All right, so then he begins to look at. I feel like something's lost here. No, okay, it's coming. It's coming. Give me a second. We'll get to it. So deflection via gravity. All right. So he, eventually we're going to actually state the wave equation. We haven't stated it yet, obviously. But his next thing Kara looks at, is deflection due to gravity. So, I mean, the larger discussion here is what's called gravitational lensing. The fact that gravity bends light around objects, massive objects, right? And so here's the here's the picture that is on page 288. Let me zoom in a bit. So he's comparing the hypothetical background path that the light would travel, right? This dotted line, x upper parentheses 0 mu, against the deflected path that's happening because of gravity, all right? And describing it in terms of this deflection angle alpha hat, all right? That's the as he says, it's decomposed the background geodesic and a perturbation x1 mu. The deflection angle alpha represents minus the amount by which the wave vector rotates along the path. A single mass m with impact parameter b is depicted. So this impact parameter b, it's the distance, the hypothetical distance, perpendicular distance from the mass and the line of closest approach for the geodesic in the flat background that it would be. So like if there was no gravity and it just was going straight away, that's how close it would be. That's the so-called, the meaning of this letter B that appears in the upcoming pages, all right? So, let me zoom back out here before I regret things. All right, and then, all right, so, wonderful. So, deflection by gravity, he writes this equation. Again, this solves the geodesic equation of the background, and this is the response to the perturbation. And this is the path of some photon or other massless particle. And so if you define, this is the, so the 4 vector in this sense is called the wave vector. So the wave vector of the background, the wave vector of the perturbation. And on page 289 to 291, he derives the formula that the deflection angles 2 times the integral of the transverse derivative of phi ds. And more to the point, for a point mass, all right, for a point mass with a background path along x, this works out to 4 pi gm over b. This is how general relativity predicts light will be deflected if it tries to basically go by something distance b from its center of mass, and the mass is m. All right, so this was one of the first, supposed experimental triumphs for general relativity that history has now started to kind of cast some aspersion on. For a few decades, I guess now, there's been people kind of poo-pooing this result, but Sir Arthur Eddington in 1919, during a total eclipse, measured, the deflection angle with respect to the sun, all right, and he measured 1.75 arc seconds of deflection. But people argue that the experiment was perhaps too imprecise to support the claim. But anyway, so since then, gravitational lensing is now an active area of astronomical research, and so this is, we're doing a lot better than Sir Arthur Eddington was back in the day. And in fact, people have gotten so confident in it that they think they can, give estimates of mass. They can kind of, if you play these games, then maybe you can get estimates of mass in terms of how the mass is deflecting the light. You could play that game if you knew enough else going on here. But I don't know. These kinds of interconnected systems of inference is a house of cards that may fall down at some point. But anyway, it's fun to think about. And let's see here. So the wave vector of a photon, it's not, it has to have, invariant product equal to, this has to be 0, which means that the time and the space components are linked, and particularly the square of the temporal component has to be equal to the dot product of the spatial components in that sense. So I think we'll come back to that in a second here. All right, so gravitational wave solutions. So if we turn off the energy momentum tensor, right, then what equations do we have? Well, we have the Laplacian of psi is 0, the Laplacian of, excuse me, good gracious, the Laplacian of the vector is 0, and from the trace of the IJ equation we have that the Laplacian of phi is 0, so only the strain tensor remains. The D'Alembert of the strain tensor is equal to 0. And if we look at the transverse traceless gauge in the perturbation metric, then the notation for that is HTT mu nu. At least that's the notation in Carroll. I think in most other books this is just H, but anyway. Oh, what do I know? But 0, 0, 0, 0, 0, 0, and then twice the strain. So it's just explicitly indicating that, you know, the strain is really the interesting place to understand what's going on with the gravitational wave. And so this equation, when you unravel it, it gives you these, these is subject to these conditions. The traceless gauge, the transverse traceless gauge involves all of these constraints over here, right? So, and then the beautiful thing is we can actually write down a formula. We can actually solve this thing using one of my favorite bits of mathematics, the imaginary exponential. So you can write down what are called plane wave solutions, and the plane wave solutions, you just take any old, your favorite constant tensor, c mu nu, times the exponential of I k sigma x sigma, all right, where c mu nu is a constant symmetric traceless 0-2 tensor, in the sense that it has to satisfy these here conditions, right? Well, these conditions are forced on it by the transverse traceless gauge condition. All right, so that's the traceless, and this is, I think, that one. But okay, so we can try it out. Like, does it work? Well, calculate the D'Alembert of this alleged solution. What happens? Well, if you calculate the derivative of the exponential, the chain rule gives you the exponential times derivative. Goodness gracious, derivative of the inside function. But that just gives me back Kronecker delta mu sigma, which gives me a I k mu. Right. So differentiate this, pulls out an I k mu. Differentiate again, you pull down another I k mu, basically. So when I differentiate this 2 times, I get an I k alpha and an I k beta. All right. And then when those are I times I is minus 1, and you end up with the contraction of the wave vector against itself times, well, this again is this times that, right? Uno momento. This is right here times this right here is precisely the alleged solution. So we have the alleged solution times something is equal to the D'Alembert, and so if this is going to be 0, either you need this as 0 or that 0, but we don't want that to be 0. For non-trivial solutions, right? For non-trivial solutions, we'd need this to be 0, right? In other words, the solution is light-like. So that's pretty cool. The natural solution here to the linearized gravity problem, which we'd understand to be gravity waves, right? They travel at the speed of light. So. Now, let's see here, what else can we say? So we write k, the wave vector is the frequency times the old traditional spatial wave vector. And it requires then that omega squared is Kronecker delta ij k like this. So for our solution, Carroll remarks, well, anyway, this is how it has to go for our solution, because we just found that the wave vector is light-like. Now, Carroll remarks that the solution is not unique, and we can superpose infinitely many such solutions. So you can add these kind of plane wave solutions together to create more interesting solutions. Let's see, and if you enforce transversality on this perturbation on our solution, well, then we have that the contraction of c mu nu against the wave vector has to be equal to 0. So let's be more specific. Suppose the wave is traveling in the x3 direction. In other words, your wave vector looks like this. WOOC3. So k mu is, omega 0, 0, k to the third power, all right? Which has got to be omega 0, 0, omega. And if we have this equal to 0, and we know that C0 nu is equal to 0, that means that C3 nu equal to 0 from this. And so then only the space, like the 1, 2, 1, 1, 2, 1, or 2, 2 could be non-trivial. And since C mu nu is both symmetric and traceless, that leaves you this. So you got zeros padding the 0 and the 3, and then you've got these middle components. They have to be minuses on the diagonal, and they have to be equal on the off diagonal because of the symmetric property. So in short, a plane traveling in the x3 direction is completely characterized by C11, C12, and omega. And so on page 296, Carroll describes how the plane waves move nearby particles in terms of the geodesic deviation equation. So this is the geodesic deviation equation. I don't know if I actually went into that earlier in this course. I'm sorry if I didn't. I might not have, but you can, I think it's, as with everything else, there's lots of details in Carroll if you go look. But anyway, you get this equation, and let's see here. You get, so he then defines, my bad, I scooch down here a bit. He defines H plus and H cross like so, and puts the tensor for our plane wave equation in this format. And the labels are made to indicate motion caused by the respective modes. So for example, if H cross is equal to 0, then we should solve these equations for the, what's the word? For the geodesic displacement, geodesic deviation equations. All right, so this is how it moves particles, basically. And so the solutions to these equations have the following form. And if you look at it, what's going on is it's taking the one component of the, it's moving it in the one component, and it's moving, it's changing the two component in the two direction. Like it's basically oscillating in the one and also in the two. All right, and so he has a picture of this, which I think is very helpful because I am not endeavoring to recreate it here. So here's his picture of what that solution would kind of mean for particles. So this, if the cross is 0, which means the plus is not, all right, then if you have this ring of particles and you study its motion, it's going to be like stretching out up and down and stretching out side to side, right? So it's this kind of vertical and horizontal squishing. Now, I think he describes that actually the specific motion of the individual particles is like in little epicycles or something, but the net motion is in this sort of plussing pattern. All right, and then on the flip side of things, you could put H, let's see here, zoom back out. On the flip side of things, you could also do this, but put the H plus be 0 and the H cross not be 0, and you get this time oscillation from 1 to 2 and from 2 to 1. And so it's oscillation in kind of like along an X. All right, so, and that he has pictures for as well, which I will show you. So here's the X pattern. So if you can kind of imagine it, you know, you start out with this ring, the perturbation, the gravity wave goes by, right? And what does it do? It has the effect of making this ring of particles stretch out like along either the line y equals x or the line y equals, well, y equals x or y equals minus x, right? So it's like a cross in the oscillation, something like that. And then, so as you said, the above solutions suggest, oh good grief, I am my own worst cameraman. There we go, I remembered though, before doing it. So you have these two sort of fundamental modes, and you could, he says you could use these to build left and right circular polarized waves in that regard. But anyway, if you just look at the plus and the cross and the plus, those are explicitly, quite clearly invariant under 180 degree rotations, if you think about it, right? If you just either flip it like this or flip it like that, right? Reflection, so they're 180 degree rotations, they're invariant. And so this actually tells us that the spin of the graviton is 2, because you can get spin from 360 degrees divided by the, let's say the maximum, well, let's see, the smallest angle which the solutions are invariant under, something like that. So the fact that we can flip the gravity waves over 180 degrees indicates that we're dealing with something with spin 2. And of course Carroll uses this as a jumping off point to talking about quantum gravity and string theory and other things at the end of this chapter, which is really interesting. And so let me just kind of share some of those points with you here. I don't want to write them out, but just to tell you a few things. So, of course, the interesting thing, actually, he doesn't say that here. I've read, I can't remember where I've read what in this book. But, I mean, of course, it is known that one of the interesting things about, string theory was originally a theory for describing a possible, I guess there's various ways it was discovered, but certainly one of its early origin stories involves trying to describe the physics of quarks, and in the process of doing this, they found that their theory necessarily included a spin 2 object. And so, there's not a lot of spin 2 objects out there. So it just kind of yells at you, this is the graviton. So they weren't looking for a theory of gravity, it just kind of came to them, and, well, the rest is history, I suppose. But okay, so what he does talk about in chapter 7, though, is the production of gravitational waves. So like on page 300 to, let's see here, 305-ish, no, 307, he describes how to go through what we just went through at second order, and he looks at Green's functions for the differential equations and talks about how to solve those things, does some Fourier analysis to, like grapple with the equations that are involved here, and ultimately finds his way to a quadrupole formula, which puts the linearized gravity as proportional to the second derivative of Iij, where Iij is the quadrupole moment tensor. All right. And then he actually gives explicit formulas for the quadrupole moment tensor for a binary star system with a relatively beautiful system of coordinates, and he actually concludes the section with an explicit formula for the linearized gravity spatial tensor for a binary star system. So that's kind of neat. So I welcome you to read those things, of course. And then page 307 to, let's see here, 307 to 315, he's talking about energy loss due to gravitational radiation. And let's see here. So I'm not sure what I can glean from that to tell you quickly. He does come to some interesting conclusions in this section, as I recall, from a physical perspective. Where is it? He says, I guess the conclusion of the section is a little bit interesting. He says, of course, energy loss through the emission of gravitational radiation has been observed. In 1974, Hulse and Taylor observed a binary system, PSR 1913 plus 16, in which both stars are very small, so classical effects are negligible, or at least under control, and one's a pulsar. The period of the orbit's 8 hours, which is extremely small by astrophysical standards. And the fact that one of the stars is a pulsar provided a very accurate clock with respect to the change in the period as the system loses energy. It can be measured. And the result was consistent with the prediction of general relativity for energy loss through gravitational radiation. That's pretty neat. It's fascinating the kind of star systems that we've found and various things we think we can say about them. And at the same time, this giant gaping question of dark energy, which says something is fundamentally wrong. So anyway, let's see here. And then he talks about the detection of gravitational waves. And I think when this book has been written, they weren't yet discovered. And I believe since this book has been written, we have observed gravitational waves. I think it was with LIGO. So that is on the cutting edge of of things. Even now, I'm pretty sure we don't. I mean, it takes incredibly violent, astronomical events to create a gravity wave large enough for us to detect it. But they are within the realm of detectability, and so he describes the interferometry and so forth that's needed to observe some of these things, as well as some of the ground-based strategies versus the giant triangular space array, the LISA. I don't know if we ever put that up. I feel like maybe not. But I haven't followed science news very carefully, so don't listen to me. But anyway, that's chapter 7 in Carol. Let's take a stroll down memory lane and see what my general relativity course at NCSU, circa 2001. So this is from these are notes I took in my class under Dr. Arkady Kafitz, who was a wonderful professor, a student of Wheeler, no less, a brilliant man. I believe he solved quantum gravity, actually, mathematically to his liking, but then disappointingly didn't have any predictions. So it's like you found a mathematically consistent thing, but it didn't have any predictions. So it kind of I don't think many people know about that, but I heard about it. Anyway, so his approach here. And any errors in this, of course, are due to my note-taking. They are no way a reflection on Dr. Kafitz for sure. But, so he starts out pretty much the same, Minkowski metric plus a linearized piece. He talks about the fact that you could do a Lorentz transformation and you'd still have this decomposition. So there are many coordinates that will satisfy the weak field condition. And he says, Riemann, keep only linear H, the rest die, so you get to that, so he gets to that pretty quickly. He says, well, you can do a gauge transformation, you can replace the coordinates and the local Lorentz transformation, I think, like so, and you have this freedom, doesn't change the curvature, doesn't change the physics, and after some calculation, you can see that. So this is the gauge freedom, because you can put any kind of swiggle mu nu you like here, and it's not going to impact the curvature, which is where we actually measure physics. All right, so then the weak field approximation. So you raise how to raise the index, the trace, both indices up. Talks about tracing. All right, and then he says, well, you can show. So I guess he was getting impatient at this point. Anyway, jumping ahead, you can show that the Einstein tensor has this form, plus order that. And then his question is, we can impose a condition to kill 3 terms, in particular this, the Lorentz or gauge, or the harmonic or Dedander gauge condition, like so. And if we do that, that gets us to this, which then just becomes that the Laplacian of squiggle is this old. So let's see, the equation has solution provided sigma's squiggle is reasonable. Solution's non-unique because that's 0 implies this is still giving you the same derivative of the linearized metric. He says, so we'll hold H subject to the Lorentz gauge. All right. And thus, Einstein's equations become Einstein tensor is minus 1/2 D'Alembert of H mu nu equal to that, which gives us the D'Alembert of H bar is minus 16 pi T mu nu. These are the linearized gravity equations. So he says we can find plane wave solutions, polarization, etc., even quantize, and find the graviton is a massless spin 2 particle. One explained the field in Fourier series. So this sentence that I wrote down, that Dr. K. Fitz said in class, I tried to write down everything he said. That's all in Carroll. Right, it's all in Carroll, man. It's such a great book. Anyway, the Newtonian limit. So we have these, small speed, small potential. The rest mass is much larger than the other terms in the stress energy. You get this equation from, I think, Einstein's equation. And impose these conditions, some calculation. We get to this metric, and that metric, which you might recognize, right? That's the metric we had in Carroll. And this one is, I think that's a Schwarzschild metric, isn't it? That's probably a sign error. I supposed to say the minus there. I would wager that I have a typo here, but anyway. So he was, when in this course, he was doing he did the Schwarzschild solution before and after this, so he's still in the process of discussing it. But anyway, it's kind of fun. Well, that's all I got to say about gravitational waves. It is a deep and interesting subject. To properly do it, you'd have to get into all of that Fourier analysis stuff. And but I think that I have given you a pretty good sense of how we can see gravity waves from a straightforward consequence of solving Einstein's equation in a reasonable context. And so there it is. See, that's something, just to context here. That's something that was not possible in Newtonian gravity. Newton never explained how gravity got from one place to another, or how would gravity change if you moved something. See, Newton's universal law of gravitation is silent on the issue of dynamics. It's for static gravitational fields. And we think Newton was aware of this, he just didn't know how to fix it. It's like he understood that there was a shortcoming of his theory of gravity, but, a theory of gravity is better than none, right? So, well, I guess there was, you know, the ancient Greeks with their, you know, love of their own thinking. You see how well that turned out. I mean, it kept us in the dark about how the universe really worked for about 2,000 years, you know. But, I mean, the Greeks did have some good math. Let's not say too much bad about the Greeks. But anyway, next up is the, what is it? Oh, yes, next we're talking about cosmology. So that should be fun. Anyway, thanks, guys.